Well, the United Nations projects that by 2050, another 2.5 billion people will be living in cities. In the United States, 60% of new home construction takes place in new developments. And, thank you. And as Rod Duridan reminded us last night, California is expecting another 25 million residents over the next 25 years. So why are we focusing all of our attention on retrofitting Podcar systems into existing cities? It seems like the low-hanging fruit might be to look at these new developments. After all, a Podcar city isn't just a car city with a Podcar network grafted onto it. It could be, or at least I think it should be, reimagined from the beginning as designed from the beginning around Podcars so that the ground level can belong to pedestrians and cyclists. At the risk of stating the obvious, I think we can agree that people will walk more if you give people nice places to walk. Like this. This is downtown Disney in Anaheim. It's a beautiful example of an urban space that's been designed around people instead of cars. There are a lot of other reasons to start with deploying Podcars in new environments, in new developments. You don't have to build expensive construction barriers. You don't have to do your construction in the dead of night. There's no need to disrupt people's lives or their livelihoods. You don't have to relocate existing lighting, signage, utilities, and landscaping. You save the expense of building all that automobile infrastructure. And best of all, when you're starting with a clean slate, you can imagine new ways of building that would never have occurred to you otherwise, like this single-level Guideway network here. It has the advantage that there are no 90-degree turns here. They're all 60-degree turns, and as you know, the tighter you take a turn, the more you have to slow down. So you can actually go a little faster on a network that's configured like this. This is what I've been working on lately, just trying to come up with ideas to hopefully get architects and city planners thinking about the possibilities of designing from scratch around Podcars. Most networks are configured like this as groups of intersecting loops. And this has the characteristic that you get a nice straight shot if you're traveling east-west, but if you're going north-south, you get this zigzag. You can reorient things like this, and then you get a nice straight path if you're going north-south, but if you're going east-west, there's that zigzag again. But if you split the difference between those two, like this, now you get a configuration where, whether you're going east-west or north-south, you kind of have not exactly a straight shot, but pretty close to it. It certainly doesn't take you very far out of your way. And in this case, the turns are only 45 degrees, so you can go a little faster still. I began this kind of project with the idea that we would be doing pretty well if we could have a Podcar station providing on-demand service within a 5-minute walk of any place. After all, most cities that have really good transit have large areas that are not that well served. But I had this nagging concern. In a car-free development, it's not really transit that we're competing with, it's the automobile. And I've noticed, as you probably have too, that when people pull into a large parking lot, they don't take the first parking space they see. And even if there's lots of space available at the far end of the lot, they don't go there. Instead, they drive up and down the aisles looking for the one space that's closest to their destination. And if they manage to get the spot that's closest to the doorway, that's like winning the lottery. And then, of course, they walk into their gym and walk on a treadmill. So go figure. I decided I needed to understand this a little bit better. So during this last year, I visited 4 gated resort communities in Florida. They were all very different, but they were all very much the same in their transit patterns. They all had a 10-mile-per-hour speed limit. People would drive there in their car. They would park as close as they could get to their unit. But once there, they would get around within the community in a golf cart. And I observed that even people who had no difficulty walking would use their golf cart even for trips that they could have walked in just 2 or 3 minutes. So imagine me walking around a resort community with a stopwatch, but I do that. I guess I am a nerd. So I concluded from that Americans hate walking even more than they like to go fast. So that got me thinking about the traditional offline station at about 330 feet long is actually just too long. We couldn't get the stations close enough together. And so I started looking at other, well, I'm going to say, I skipped over something here. I think this is a good example of how you can't really separate out technology and innovation. Steve Jobs used to say that technology and liberal arts is the intersection where interesting things happen. And this was kind of the point at which I kind of got shifted off of the design, where I realized I was going to have to look at some of the underlying technology here, like, well, I skipped over a slide here, sorry. This thing here, this is the perpendicular station. These have the advantage that you can get a little bit closer, stations a little bit closer together. They reach out further into surrounding neighborhoods. But they also have the potential advantage that they can be done with less guideway. That's because as you turn off the main guideway, as soon as you're clear of through traffic, you can begin to slow down even before you've finished turning. But that means that this is not a simple spiral turn, and I needed to make a computer model, a visual model of this, an architectural model, and I realized I didn't really know exactly what the shape of this turn was. So that kind of got me sidetracked onto this issue of having to go from the world of design into the world of technology. So this will just take a brief moment here. I don't want to get too technical, but here's a nice smooth velocity curve. But you can't feel velocity. What you feel is the rate of change of velocity, which is acceleration, and the rate of change of acceleration, which is called jerk. So the acceleration is just the slope of this curve at any given point. So here is the corresponding acceleration curve. But too much acceleration could frighten grandma. So the American Society of Civil Engineers published an automated people mover standard that sets comfortable limits for acceleration and jerk. So that's why we have this flat part here at the top and also at the bottom. We kind of increase the acceleration to the point where we think it's as much as is comfortable for people, and then we stay at that constant acceleration until we back off from it. Here we've set the... Per second squared? Yeah, this is actually, it's miles per hour per second squared. Actually, miles per hour per second. The jerk is miles per hour per second squared. So here the acceleration has been capped at 90% of the maximum that is allowed in the APM standard. The jerk is just the slope of this curve at any given point. So here is the jerk curve, and that is again capped at 90% of the maximum that is allowed by the APM standard. So the point of this, I've just so far been looking at the forces in the direction of movement, but this same principle applies to forces from side to side or up and down, and if you combine all three of those along with the interactions between them, you can derive a shape for that turn for the perpendicular guideway that will feel just as smooth as glass as you go over it. I want to go back just briefly to this velocity curve again for a moment. This is, of course, a kind of idealized computer-generated curve. But the amazing thing about these is that a Podcar can actually do this. A well-designed system, if it's not overloaded with traffic, can be built in such a way that you could put an accelerometer in a pod, put it through its paces, and you will get a curve that looks pretty much just like this. To put that in perspective, I'm going to redraw this same curve here at a different scale and extend it out for a trip of 7.5 miles. And then for comparison purposes, I'm going to add this other curve. This is the urban dynamometer driving schedule. This is the driving pattern that's used in the United States, Sweden, and Australia to test the mileage of a car in city driving. It's been very carefully crafted to be a faithful representation of the kind of driving that people typically encounter in cities. So this chart, I think, dramatically shows two really interesting things. One is why podcars are inherently more energy efficient than just about anything. The energy that goes into propelling a vehicle is basically used to overcome two forces, inertia and wind resistance. So the inertia, if you've ever had to push a car, you know that you really have to put your back into it to get the car moving. But once it's going, it's not too difficult to keep it going. So all of these areas in both of these curves where there's an upslope, that's where you're having to overcome inertia. So you can see with the Podcar, we basically accelerated to speed once. We can cruise at that speed continuously until we get to our destination. All of this stopping and starting in the automobile driving pattern is using tremendously more energy to overcome inertia. The other main force that you're trying to overcome is wind resistance. And wind resistance has the characteristic that it goes up as the square of velocity, which just means if you double your speed, you get 4 times as much wind resistance. So here at the peak, towards the left there, the car is getting to be almost 57 miles per hour. At that point, it's using more than 8 times as much power to push through the air as the Podcar at the same time. So all of this part of the automobile curve that's above the curve for the Podcar is using tremendously more power to push through the air, and it's not saving anywhere near that much in the part where the car is stopped. So the other major thing I think that this chart shows is why Podcars are inherently better than self-driving cars. The proponents of self-driving cars are declaring quite proudly now that they can now do this. Right? They can stop if a car in front of them stops. They can stop if a car pulls out of a driveway in front of you. They stop for pedestrians, for bicycles, stop signs, traffic signals. They're really good at stopping. But of course the problem is that when you're in a vehicle, you don't want to stop, you want to go. And that's what Podcars do better than anything. The Podcar, you can see, even going 20 miles per hour, it actually finishes a little bit ahead of the car here, because the average speed of this driving curve is slightly less than 20 miles per hour. So our best bet are still Podcars for sustainability, for safety, and for creating a more humane urban environment. There's still a lot more work to do here to figure out ways to get Podcar stations closer to people's doorways and to come up with new architectural designs that get people's doorways closer to Podcar stations. But I believe no matter how you look at it, you're going to find it much easier, less expensive, and get a better result by designing Podcar cities from scratch instead of retrofitting. Thank you.